Yeah, thanks to Sergey for the introduction. And it's so great to be back in Barcelona for the second iteration of Wasm IO. And today I want to talk to all of you about the WebAssembly Component Model to give you a high-level overview of what it is, why you should not ignore it, and then spark some ideas of what you can build with the component model as of today. So that being said, my name is Thorsten. I work as a cloud advocate with Fermion. If you want to talk to me about the WebAssembly component model or server-side WebAssembly in a whole, then find me at the booth or shoot me a mail or reach out on X. So that being said, let's jump right into the topic. So the WebAssembly component model, what is it? If we look at it from a very high point of view, the WebAssembly component model is just the addition to core WebAssembly that addresses some shortcomings that we have when we work with WebAssembly modules, and it dramatically streamlines how we can interact with WebAssembly modules, no matter in which language they have been written in. So you can think of it basically as a proxy or wrapper around your WebAssembly module. And that proxy takes care of defining a so-called canonical ABI, which takes care of specifying and standardizing how data is laid out in memory in a unified way that all languages adopting the component model agree on. And this ultimately gives us a richer type system. So we can use strings, objects, or you may call them structs, lists, or vectors. And it does not matter anymore how the original language is laying out that structure in memory. That's all done by the component model, and it's taking care about the conversion so that we all can agree on a unified interface of those components. So speaking about the interface of components, we can use WebAssembly interface type language, or short WIT, to define richer contracts, making use of those types that we can now use to communicate between different components. So ultimately, the WebAssembly component model simplifies using components written in different languages. So we don't have to agree on how component A laid out string in memory in contrast to another component written in a different language. So if we, for example, take a look at an application written in Spin, we have the Spin runtime. In the case of building an HTTP API, the runtime imports WASI HTTP incoming handler, and as every Spin app is a WebAssembly component, it is also able to export capabilities. And in the case, again, of an HTTP API, the Spin application component exports exactly that incoming handler function. But we can take that one step further, right? We can add additional imports to our Spin application component or to our WebAssembly component and bring in third-party or custom components, fulfilling those imports by providing implementations for the contract. At the end, we have language-agnostic tooling that we use to compose both components together into, I refer to it as a composed WebAssembly component. So that is ultimately the final application that we are able to run. So having a rough idea of what the component model is, I want to talk to you why, or I want to tell you why you should not ignore it. And this morning, Chris already did a history lesson, right? But we share one reference. So the first mention of components was in 1968 by Douglas McElroy, and if all of you have been to the session, then you know the details of that. But from that point in time, we were undergoing several areas or iterations of specification and implementations of component stories or component models. So over the years, developers gained productivity because they were able to build apps faster by taking existing components and composing them together to become an application. And there were numerous technologies being really successful by providing a component story or having something in place similar to what the WebAssembly Component Model offers us in the world of WebAssembly. So the list of technologies is really long that came up with a component story. So I choose a few to put on that slide, so don't judge me for that. Back in the 90s, we were all using Windows desktops. I think Linux for desktop was already a thing there. But basically, what Microsoft came up with was COM in 1993, and in 1996, it was ActiveX. Right? ActiveX had that idea of bringing components to different platforms. However, 98% of the components were only available for the Windows platform. So a couple of years later, the ASP.NET team took that idea of components and baked it into something that's called the Open Web Interface for .NET, or short OWIN, which was basically a mechanism of plugging in different components, like middlewares, to construct HTTP responses. But I bet most of you have heard of web components, taking that idea of composition and components to the native web, so leveraging only native web technologies that allowed front-end engineers to compose rich user interfaces. So you may have heard the term micro frontends, which are basically those components. We don't care at that point of view which single-page application framework or which JavaScript framework was used to craft that particular component. They all agree on a model how they can talk to each other and interact with each other. So it is kind of impossible to talk about components and not showing some components, right? So let's start in the 90s. We had rich user controls and components that made us able to build shiny UIs, but the idea of components is not limited to UI components, right? We were able to take logical components and extend the capabilities of applications. And if you look at that diagram, that's again illustrating how ASP.NET worked once they got OWIN, once they shipped OWIN. So we could bring in components or middlewares written by third parties, maybe by component vendors, and compose our HTTP APIs to react on certain things when they look at HTTP requests hitting the server. Okay, so that's all about history, so let's talk about the present, right? So I think we all agree that WebAssembly itself makes apps portable across platforms and architectures, right? So I really want to emphasize that the WebAssembly Component Model takes that portability to a whole new level. So by adopting the component model, we were able to make components portable across programming languages without caring about the nitty-gritty details in terms of how things are laid out in memory when one is using Rust and the other one is using Node.js to build components. All right, so that being said, let's have a look at what you can build with the component model as of today. Before we dive into the demos, we want to quickly rush through tooling. So I looked at the tooling space, and I try to distinguish the tooling space in two different ways. So first, we need language-specific tooling. So that's the tooling that helps us as developers, going from our source code to WebAssembly and then wrapping that into a component in order to make it usable or consumable by other components. And we have, like for Python, there's componentized Py. For JavaScript, we have, for example, JCO and componentized JS. And in Rust, when you're building WebAssembly components with Rust, you can use cargo component to compile your Rust code to WebAssembly and then package it as a WebAssembly component. So at some point, we end up with a WebAssembly component, right? So we need some kind of language-agnostic tooling to poke around with WebAssembly components. And there's, for example, Wasm tools, which give us the capability of composing richer applications by, merging together different components and forming an application. We can also use, for example, the Wasm tools component with command to inspect which particular contract a certain component actually implements. But besides Wasm tools, there's also WebAssembly Composition, or short WAC, which is another CLI that not just takes care about composing applications from multiple components, it also provides a domain-specific language that you can use to specify the composition in a declarative way and approach it in a different manner, right? So there's an ongoing discussion about if and how WAC could be integrated into Wasm tools. So if you're interested in that one, you should definitely take a look at that GitHub issue mentioned over here. All right. So I think that's most of the slides. Let's move into 2 sample applications. So first, we were looking at a host application. That one is written in Rust. And the idea of that application is to take a user input and apply some transformations to it. However, the developer decided not to place the transformations in the host application itself. Instead, he or she came up with an extensibility world, so this is a with contract, right? Importing a transform function that takes an input as string, does some computing, and returns back a string again. So then, with that in place, we can come up with plugins using the WebAssembly Component Model implemented in different languages. All we have to do is all of those components have to implement the plugin world which exports exactly that function that the host is importing. So ultimately, the host can load all the WebAssembly components, iterate through them, put them in a chain and call the transform method one after another. Okay, so let's have a look at that one. And let me quickly bring up VS Code over here to emphasize which language we are looking at. So first we start with Rust, right? So let's write the host application. Let's have a look at the host application. All right, so this is a regular Rust binary crate, and it has a dependency to wasm time with the component model feature activated, right? We have the world of extensibility over here importing the transform function. From implementation point of view, wasm time with the component model feature makes it pretty straightforward to iterate over plugins. We will load them from a folder on my disk, right? So we iterate over all those files. We create a component from every file. We instantiate the component over here. We check if the component actually provides that transform function. And if so, we invoke that function over here. Finally, when the WebAssembly component returns back the result, we take the result and hand it over to the next component in line. All right, so speaking about plugins, we will look at two plugins. So now let me do the plugin developer, was also using Rust. So I was using cargo component tooling to create a new Rust crate, a library crate, in that case, which gave me, some dependencies pre-configured in my manifest, and also provide some package specification over there. From a contract point of view, I grabbed that plugin world and I just implemented the transform function. So implementing the transform function is pretty straightforward, right? We have a component struct over here and we implement the guest trait. And the guest trait is basically taking the input as a string, applying the toUpperCase method over here, and implicitly returning the result back as string. So we can use rich types when implementing contracts and packaging our modules using the WebAssembly Component Model. All right, so, I need that in a second. Let's have a look at a different one. So green, some people may guess, green is the color of Node.js. So let's have a look at the reverse plugin. So I'm now impersonating into a JavaScript developer, and I'm used to the ecosystem that JavaScript provides. However, reversing a string does not need any kind of NPM module, hopefully, right? So what I got, again, the plugin world that I have to implement. And then, from that point, I would just write Node.js or JavaScript as I would normally do it. So I check if the input is truthy. So in the case of null, or an empty string, I simply return it back. If the value is truthy, then I split it, reverse it, join it, and I return back the result. However, for JavaScript, we will have a look at, not the README, sorry. We will have a look at what happens at build time. So first, in line 7 over here, we use language-specific tooling to take our source control, compile it to WebAssembly, and package it again as WebAssembly component. I then use language-agnostic tooling to shrink that component a little bit, but that's language-dependent in that case because JavaScript components or modules try to they are a little bit bigger because we have to ship a bit more than just our JavaScript file. All right, so let's have a look at that in action. And I have to take off the hat again. All right, so on the left-hand side, let's do a make run. So this starts the host. And the task is to transform the input. So let's provide an input. And as you can see, hey, I did not found any transformers, so I'm returning the string as is, right? So on the right-hand side, let's now use a make build all plugins. That iterates over all the plugins, creates WebAssembly components from the source, and then I can, activate plugins. Activating plugins is as simple as copying the desired plugin into the active folder, moving back to the host application, and again, transforming foo, and we get back an oof. Okay. Now, let's take another plugin or component, copy that over, and again, let's invoke that one, and finally, we get back a big oof, right? Cool. So that demo basically illustrates how you could build components to roll or use WebAssembly Component Model to roll your own extensibility story and load those components dynamically at runtime. All right, So let's go back to the slides, because I want to show another demo where we were looking at a slightly different scenario. So consider having two apps, right? There's the Acme service. So that's an HTTP API or a product providing third-party integrations via webhooks. So third parties can register and express their intent in being informed if interesting or when interesting things happen in Acme. So as you can see, Wonka is a Python service that gets notified every time something interesting happened in Acme. At some point in time, folks at Acme decided, hey, you know what? We want to be a little bit smarter, so we want to sign every outgoing payload with a customer-specific key data or key material, right? So that the consumer or the customer is able to verify integrity of the payload sent or received from Acme. So taking that requirement and coming up with the corresponding WIT contracts is fairly simple, right? So at Acme, they have somehow to sign arbitrary payloads. On the flip side, every consumer of a webhook must somehow be able to verify the integrity of a payload to ensure he or she is not facing a man-in-the-middle attack, for example, so where someone modifies data while data is in transit. All right, but you know, product managers at Acme were a little bit smarter. They said, hey, instead of just coming up with the WIT words, we built a single component, and yeah, we implement that one in Rust, but with that, we can, we can hand over the WIT contract and the implementation to all our webhook consumers. So no one has to implement HMAC signature verification on their own because we provide a default implementation. All right, so let's jump back to the demo. And let me think, yeah, we start again with Rust. Alrighty, that's this. And let me hit play over here. So now we can have a look at the HMAC component, you know, that thing at the bottom of the slides first. So we define a world, the world of signing. And in the realm of signing, we have both capabilities. So we have the sign and we have the verify functionality that we export. So our component implements that and exposes that functionality to the outer world. We obviously have to instruct our programming language, in that case Rust, so we update the cargo toml and provide some fundamental metadata about the package itself. From implementation point of view, it is again the same, right? We have that struct that simply has to fulfill that contract, and we do so by implementing both traits. So we have the sign trait, which we use to sign a payload, and we have verification trait that we use to verify the integrity of bytes. All right. Speaking about how to build that application, again, we use language-specific tooling over here to take that source code and come up with a WebAssembly component. All right. Now, let's flip the head again. Now, let me act as the application developer at Acme. So again, we also use Rust. So we build our WebAssembly applications using Spin. Basically, our product exposes HTTP APIs. So for example, there's a registration endpoint which third-party application providers can invoke and express their intent on being called if something happens, right? Upon registration, we generate random key material and send that back to the callee so that that particular entity could store that key material in their data storage of choice and use that from that point in time to verify the integrity of the payloads they receive from us. On top of that, there is that fire endpoint that we will invoke in a couple of seconds, right, to simulate something interesting happening in our application. So again, this component, the Acme service, I as the developer of the Acme service, I'm only interested in signing payloads. I don't care at this point in time of verifying the integrity, right? So I import the sign capability from the HMAC component. Obviously, I have to tell where tooling could find the HMAC world. And from there, when something interesting happens, I come up with a payload, and then I simply call the sign function, and from that point in time, we send the tag, so the signature for that payload, along with the payload as an HTTP header to the callee. This time, the build instructions are a little bit more interesting, right? Because we have the HMAC component is already built, so we have that. So we use cargo component build to build our spin application, and then we use language agnostic tooling to compose the final application by merging together the HMAC component and the application component. All right, that said, I have to switch heads. So there's a blue one. Now let's have a look at Wonka. Right? So at Wonka, we are used to do everything with Python, right? And at some point, folks at Acme gave us this great WIT file, which acts as a contract for us to how we can verify data integrity. Along with that WIT file, we also got a WASM file, which used to be a WebAssembly component. So we took that WIT file, throw that in our project, then we import the verify function, and upon receiving a webhook, we look at the signature, so we take the tag of that so we take the tag from the HTTP request, so with the given header. Then we go to our data store, we grab the key material that we received upon registration at Acme, and finally, we invoke the verify method. If the payload is valid, then we return an HTTP 200. If the payload has been modified in transit, we return a 400. Again, let's have a final look at what happens at build time. So we use, again, language-specific tooling, componentized Pi, to come up with a WebAssembly component from our source, and then we compose together the HMAC component and the application component to form the final application. All right, so now I have switched enough heads. So let's move to the terminal one more time. So on the upper left side, let's do a make start Acme. Acme service is running on 3000, right? In the bottom area, let's do a make start Wonka. Wonka is now running on 3002. So we're using the upper right terminal to make register Wonka, which basically calls into Acme, says, hey, Wonka runs on 3002 and is interested in certain events. Okay, let's fire this thing. And as you can see at the bottom of the screen, Wonka at some point received random key material, right? And we, also the team at Wonka, decided to store that key material in their data storage of choice. So what happens when a webhook fires? So let's clean this thing up and let's make a fire webhook. So right now we are hitting that fire endpoint at Acme on localhost 3000, right? That iterates over all the registration, pulls key material for that, and then invokes that provided HTTP endpoint. And as you can see at the bottom of the screen, in Wonka we take the tag, we take the random key material, we verify integrity, and ultimately return HTTP 200. And with that, let's quickly jump back. There are 2 more slides. So there are some key takeaways that I hope all of you got from that talk. That's basically WebAssembly components are self-contained and they allow interaction or using or composing apps by agreeing on rich contracts that are defined in WIT. So we saw in the extensibility example, we saw that we can dynamically load components at runtime, and in the second example, we took a look at how we can compose bigger applications using components, no matter which language we used to write them. And the component model takes care about, translating how data is laid out in memory. With that, there's only one more thing. If you want to dive deeper on the component model, then I highly recommend Ryan's talk happening tomorrow at 12:40, where he guides you through deconstructing WebAssembly components. And with that, there's the link for the sample. Thanks for your attention and enjoy the rest of Wasm IO. Questions? Questions? No questions? Anyways, if there are questions... there's a question, yes. Do we have a mic?
Yeah, that was great. Thanks. I now vaguely understand what's going on.
Thanks.
I agree this kind of encapsulation of components into reusable things that you could then have across different services consuming. Is there kind of a best practice that you recommend around some sort of component registry or centralized storage of these components?
Oh yeah. Let's phrase it that way. There's room for improvement when it comes to the DX in order to make things discoverable. Right? I mean, there's ongoing work in Bytecode Alliance and throughout the entire community of how we can come up with a story to smoothen, that experience of developers, recognizing the WebAssembly component model and being able, for example, to discover, like you said, components or WIT contracts, maybe at a central place. So yeah, there are ideas, there are, let's say, prototypes. There is Wark, for example. So there are already ideas, but there's definitely room for improvement when it comes to discoverability, yes. More questions? Over there.
Over here. Other side.
Okay, sorry.
So what I found when playing around a bit with the generated bindings is that bindings often end up being quite unidiomatic to use in the target language. So do you expect that wrapper libraries that wrap the auto-generated bindings will be common?
Well, so if I understood your question or your sentence correctly, then you found the generated bindings being not that idiom, depending on the...
Not idiomatic for the target language, because you write your definitions, functions, and types coming from the language where you implement it often, like Rust bindings will look quite different, typings will look quite different from Python. For example, how do you express some types, Rust enums in Python, and so on. So what I found is that it often ends up feeling very unnatural for the language, which would be solvable by writing a wrapper library around the auto-generated bindings. But I'm just curious about your thoughts there.
Yeah, I mean, that's a good point. So, obviously we have to agree on a contract or on a set on capabilities that we could use in as many languages as possible. Although this may not be the idiomatic way how you would treat or build an API in that particular language, I think that's an opportunity for maybe the community to bring, additional, let's say, glue code to take or maybe make those make the generated code be more idiomatic in a way of, hey, this feels like Python code, and I'm used to use it in a particular way. But so far, I mean, obviously, it's all, moving targets, and yeah, it is what it is as of today, because we have to agree on a certain level of complexity and to integrate or to come up with bindings that work on either side. More questions? I think there was one over there.
I have a closely related question, actually. The syntax in Rust is very beautiful, but what about like more mundane stuff like C++? How do you see that? When is it coming, and what's the state of affairs?
Oh, so that's a great question, but to be honest, I don't know. I haven't touched C++.
I guess it's a question for everyone.
Yeah, but I think Till has a take on that one. It's coming. So in C exists, C++ will come soon. That's right? That's right.
Thank you.
All right. Okay. Yeah, sorry. Sorry. I thought there would be next speaker already laning up. That's why I pulled the HDMI. So yeah, the code for both examples is on GitHub. So you can find it over there. All right. You're welcome. So thank you once again, and enjoy the rest of conference.